In this video, we're going to see another example of how category theory can be used to prove results in more concrete and elementary areas of math. In this case, we're going to take a look at another example from linear algebra, and we're going to see here that the universality of quotient spaces is actually able to prove directly the first isomorphism theorem. So the first isomorphism theorem is a very important result that holds in a lot of mathematical structures, but in this case, we're going to look at it in terms of vector spaces. And we'll unpack the definition more later, but just to see the statement, the first isomorphism theorem says that for any linear transformation T from V to W vector spaces, the image of T is isomorphic to the quotient space over the kernel of T. So obviously that's a bit of a mouthful, and we'll take a closer look in a little bit, but just to see how it's written here, we have that the image of T, our linear transformation, is isomorphic to the quotient space of the vector space V over the kernel of that linear transformation T. And what is the kernel? The kernel is all of the values in V which map to 0 in W by T. So the kernel here of T, just to remind you, is the set of all of the V's in V such that when you transform V by T, you get 0 in W. So first, let's take a look at the universality of quotient spaces. So we'll remind ourselves what quotient spaces are and when do they have the universal property that we've looked at in previous videos. So let's fix a field K. And let's take V, W, and some linear transformation T going from V to W, all in the category of vector spaces over K. So V and W are vector spaces over K, and T is a linear transformation from V to W. Now take some subspace S of V, and let's define V1 is related to V2 by tilde for V1, V2 in V, if there is some element in S such that adding V1 to S gives you V2. So if there's some element of S, some vector in S, that I can add to V1 to get me to V2, then we have that V1 and V2 are related by tilde in V. It turns out that tilde is actually an equivalence relation on V. How do we know that? Well, what do we need to have an equivalence relation? It needs to be reflexive, symmetric, and transitive. So let's prove that. So first, we need to have that V1 is always related to V2 by tilde. But that's the case because if S is a subspace, then 0 is in S, right? Because it's always in any subspace. So V1 plus 0 equals V1. And that's the formula we need. V1 is related to, this should say obviously, V1. Now, next, we need to show that if V1 is related to V2 by tilde, then that means we must have V2 is related to V1 by tilde. But that's the case because if V1 is related to V2 by tilde, then we have V1 plus S equals V2 for some S in S. And if that's the case, then we have V1 equals V2 minus S. But S is a subspace. So if S is in S, then minus S has to be in S. And so we have the formula we need here. V2 plus minus S, which is an element of S, equals V1. So the last thing we need to check is if V1 is related to V2 by tilde, and V2 is related to V3 by tilde, then we have to have V1 related to V3 by tilde, and that's called transitivity. So suppose these two are the case, well then we have V1 plus S1 equals V2, and we have for some S1 in S, and we have V2 plus S2 equals V3 for some S2 in S. And if that's the case, then we can substitute this V2 by this in this formula to get V1 plus S1 plus S2 is equal to V3. But again, we can appeal to the fact that S is a subspace. So S1 plus S2 has to be in S, and so we're adding something in S to get from V1 to V3, and so we're good. We have that V1 is related to V3 by tilde, and we have that tilde is actually an equivalence relation on V. Now we know that anytime we have an equivalence relation defined on a set, the equivalence relation partitions that set into equivalence classes. So what that means is that we have a set of equivalence classes V plus S, where V is in V, which partitions the vector space V. So anytime you start in one of these equivalence classes, one of the vectors in here, and you just keep adding elements of S to it, you'll always stay within this equivalence class. And every vector is only part of exactly one of these equivalence classes, all of the vectors in V. Now, using this, we can actually define operations, vector operations, on these equivalence classes. Because we can just say that, for example, V1 plus S plus V2 plus S is equal to V1 plus V2 plus S. And if we have some constant C in K, then we can do C times V plus S by defining it as C times V plus S. And what happens is that if we take these as vectors and these as vector addition and scalar multiplication, then what we get is that this actually forms a vector space over K. And as with a previous video, we're not going to show that because there are so many axioms for vector spaces that it would take a long time. So we'll leave that for an exercise. It's not too difficult. Just use these definitions and check each one of the vector space axioms one after the other. We call this vector space the quotient space. And we denote it as V over S. So it's the quotient space of the vector space V over the subspace S. And notice that we can map any V to its equivalence class V plus S. And that mapping will exist for every V. And for every V, it will map to exactly one of these equivalence classes, right? Because this is a partition. So each V can be in one and only one of these. And so the mapping rho from V into V over S, the quotient space, defined by rho of V, is equal to the equivalence class v plus s. This is going to be a well-defined function. We call this function the canonical projection. So the canonical projection projects a vector space V into the quotient space over some subspace S. And we said in the intro of the video that these quotient spaces had a universality property, or maybe rather that there were conditions under which these quotient spaces had the universality property. So what we want to ask ourselves is this pair of the quotient space and the canonical projection into that quotient space, is this universal for the vector space V and the identity functor going from the vector spaces over K into the vector spaces over K? So this is just the identity functor that maps every vector space to itself and every linear transformation to itself. And what we want to ask is, under which conditions is this pair here universal for this pair, VI? So let's remind ourselves the definition of universality. We have our canonical projection rho here going from V into V over S. And we want to say that for any arbitrary t going from V to W, we have a unique morphism or a unique linear transformation. And normally we'd have to draw it over on this side with a functor going this way. But this is just the identity functor in this case. So we can just move it right over here. It's just going to map to itself, so no need to draw it. We can just plug it right in here. We're going to have some unique tau of t going from the quotient space into W such that this diagram commutes. And what do we get if this diagram commutes? We have to have t equals tau of t after rho. We're in the category of vector spaces over K here. And we know that this is a vector space over K, so we're good there. But we also need to know in this case, for this diagram to work, that rho is a linear transformation, because T is a linear transformation. And so if rho is a linear transformation such that this property holds, then we'll also get a unique linear transformation, tau of t. So in order to see this, we need to know that rho is a linear transformation, but it is, and that follows directly from the way that we defined vector addition and scalar multiplication on these elements here. If you remember how we defined those, it was pretty obvious, and that will directly give you the linearity of this canonical projection here. So we're good from that perspective as well. It turns out that this pair has this universality property in the case that S is specifically in the kernel of T. So if every value in S maps to 0 by T, then this universality, and S is a subspace, which was already one of the conditions we had, then this universality property will hold. And so to prove that, we need to find a unique tau of t, which is a linear transformation and which satisfies this equation. So what we would need to have is we would need to have some tau of f, or tau of t, which goes from v over s into w. And it would need to be the case that for any v in v, we would need to have that t of v is equal to tau of t after rho of v. This is just the universality equation applied here. And so if that's the case, then we would have some function tau of t that, when applied to one of the equivalence classes v plus s, would simply give us t of v. So in order for this to exist, we need to make sure that this could be well defined, because if there's no well-defined function that satisfies this, then obviously there's no universality property here. So what we need to show is that if v plus s is equal to w plus s, because remember, these vectors, even though they could be different, could map to the same equivalence class, v and w. So v and w here map by row to the same equivalence class, v plus s. And if that's the case, then we need to show that this implies that tau of t of v plus s has to be equal to tau of t of w plus s. But this is the case because if v plus s is equal to w plus s, then they have to be part of the same equivalence class, v and w, because v plus 0 has to be in this equivalence class, and w plus 0 has to be in this equivalence class. So we get that v is related to w by tilde, by the relation that we defined earlier. And what that relation meant was that there existed some s in s such that v plus s equals w. Means that v minus w is equal to minus s, but s is in s, and s is a subspace, so minus s also has to be in s, which means that it's in the kernel of t. So what we're saying here is that v minus w is in the kernel of t. And if it's in the kernel of t, then we have to have that t of v minus w is equal to 0, which means that if we break this up, we get t of v minus t of w is equal to 0, and we get that t of v is equal to t of w, which is exactly what this implies, that tau of t of v plus s is equal to tau of t of w plus s, which is exactly what we needed to show. So we found a t of v that's well defined and that satisfies the universality equation here. So in order for this universality property to be completely satisfied, we need to check two more things about tau of t. The first is that it's unique. That's part of the definition of universality. So, but it is unique because it's just t of v. So we know exactly for every equivalence class v plus s, we know exactly which value we're assigning to it, which is t of v. And not only that, but we need to also check that it's a linear transformation, because it lives here in vect k, so it needs to be a linear transformation between vector spaces. And that's also extremely easy to check. You can kind of think of it just as the fact that because it's just t of v, and t of v is linear, while tau of t is also going to be linear. But you can check it exactly, rigorously for yourself if you want to. And so we have the universality property that we wanted. We have that this holds. This pair is a universal for vi. So we've established the universality property, and we said at the start of the video that what we were going to do was we were going to see how that could imply that the first isomorphism theorem is true. And so we're going to look at how this implies the first isomorphism theorem. And what did we say the first isomorphism theorem was? Well, we said that it was that the image of T is isomorphic to the quotient space over the kernel of T. So if we can somehow use this universality property to find an isomorphism from the image of T into the quotient space over the kernel, then we've proved the first isomorphism theorem thanks to this property here. Where does this isomorphism live? Well, it's in the category of vector spaces over K. And so what does it need to look like? Well, what does an isomorphism in this category look like? Well, it's a linear bijection, right? It has to be linear because every morphism in this category is a linear transformation. And it has to be a bijection because vector spaces are set-like objects, and so isomorphisms between them correspond to set bijections. So if we can find a linear bijection going between these two objects, then we've found the isomorphism required to satisfy this theorem. Now, in order for there to be a linear transformation between these two, what do we need to check? Well, these both need to be vector spaces, because linear transformations are defined between vector spaces. So we already know this is a vector space, but we do need to check one thing first, which is that in the definition of our quotient space here, this S, whatever's on this side, needs to be a subspace of V. But the kernel is a subspace of V. So the kernel of any linear transformation is a subspace of the domain of that transformation. That's one of the first results you prove in linear algebra. So we're good for this one. This is, in fact, a vector space. And we need to make sure that the image of T is also a vector space, which it is. And you can prove that very easily. Should be 3 or 4 lines to prove that. So you can try that as an exercise if you want. So we're good in the fact that these are both vector spaces. So in theory, there could be a linear transformation between them. So how do we use this universality property to find this linear bijection here? Well, let's notice that since we said that S had to be a subspace of the kernel of T, it would be perfectly fine to substitute the kernel of T in for S here, right? Because the kernel of T is a subspace of itself, obviously, because they're equal. So I could actually use specifically the tau of T, which goes from the quotient space over the kernel of T this time into W. And since we know that the image of T is a subspace of W, and since we know that tau of T is literally just T of V, we could actually just call this the restriction of tau of T to the image of T, which has the same domain. It maps from the same space, but this time it goes only into the image of T, right? Because tau of T is just T of V. So tau of T only lands on values that T of V lands on. So this function is going to be properly defined. And if that's the case, then it's surjective. The restriction of tau of T to the image of T is surjective. And why is that? Well, this is all of the values that get mapped to by T. And for any T of V, we can just use the equivalence class V plus S to map to it by tau of T. And this is just the same as tau of T. So for any T of V in the image of T, we have a value V plus S, the equivalence class V plus S, which maps to it by this restriction mapping. So this restriction mapping is surjective. And if we look at the kernel of this mapping specifically, so that's the kernel of this restriction, that's going to be the values V plus kernel of T, all of the equivalence classes, such that when you map that equivalence class by this restriction, V plus kernel T, it maps to 0, the 0 vector. And if that's the case, well, the restriction of tau of t of v plus kernel t is just tau of t of v plus kernel t, which is just t of v. So we can rewrite this as all of the equivalence classes v plus kernel of t, where t of v is equal to 0. But if that's the case, then these are just the values in the kernel. So this is the values v plus kernel t, where v is in the kernel of t. Right? It maps to 0 by t. But what is this set here? Maybe this is a good place to pause the video, and we'll have a few exercises coming up as we go here, and so maybe this is the first one. Pause the video here to check your understanding. What is the simplest way that we can rewrite this set here? Well, it's just values v in the kernel of t plus other values in the kernel of t. So it's just values in the kernel plus values in the kernel. But the kernel is a subspace, so it's already closed under addition. And so this is actually just the kernel of t. And what is the kernel of t? Well, it's the equivalence class 0 plus kernel t. Right? It's the value that the canonical projection will send 0 to. And this is maybe the second exercise you could do, is prove this step here. I mean, it's pretty obvious based on the notation, but maybe prove it rigorously to make sure that's true. And what is this? Well, this is just the 0 vector of this space here, right? It's the one that 0 maps to. So this is just the 0 vector. And since we know that the restriction tau of t is linear, why is it linear? Well, because tau of t is linear, and it's just tau of t going into a different space. So we know that tau of t is linear. Again, because the restriction of tau of t is just equal to tau of t, and tau of t is just equal to t of v, and t of v is linear. So by that chain of logic, tau of t is linear. And what is a linear mapping where the kernel is exactly equal to 0, to the 0 vector, right? The kernel of this restriction mapping is just the 0 vector. Well, it has to be an injective mapping. So the restriction mapping is also injective. And so that's the third exercise maybe we could try. So you could pause the video here and say, why, if I have a linear mapping where the kernel is exactly equal to the 0 vector, why does that have to be an injective mapping, an injective linear transformation? But these three results together is exactly what we needed. This says that the restriction mapping tau of t to the image of t is a linear bijection. That's exactly what we needed. Now, of course, there's one last step, which is that we wanted to see that there's a mapping from the image of t into the quotient space over the kernel. But this just goes in the opposite direction, and it's a bijection. So we can just say that the inverse of the restriction mapping to the image of t goes from the image of t into the quotient space over the kernel of t, and it's an isomorphism, which is exactly what we needed to prove. We've proved the first isomorphism theorem. So this is QED here. So just to summarize, we proved that there was the universality condition of quotient spaces, specifically when the subspace S is a subspace of the kernel. And we showed that because that's true, we can fairly simply prove that the first isomorphism theorem is true, which is that for any linear mapping T, the image of T is isomorphic to the quotient space over the kernel of T. Just a couple of final notes here. One is that if T is a surjective function, right, if this linear transformation T actually happens to be surjective, then it covers all of W, so the image of T is actually equal to W, and if that's the case, then we get that W itself is actually isomorphic to the quotient space over the kernel. So that's a pretty cool result. For any surjective linear transformation T, the codomain W is actually isomorphic to the quotient space over the kernel. The other interesting note is that at no point during this discussion did we ever rely on the fact that these field elements needed to have multiplicative inverses. So we could have done this whole discussion again, replacing this field K with some ring R. And so what would the equivalent of the vector space be if we were using a ring instead of a field? Well, it would be an R module. And so this whole discussion actually applies equally as well to R modules, the universality of the quotient module, and the first isomorphism theorem for R modules. So that's a nice generalization that we get for free by proving it based on vector spaces.